Okay, I'm going to go through a puzzle in a minute, but I just want to show you something that we're going to use at some point during the puzzle. This area of maths is part of decision maths, and it's called graph theory. And I'm going to talk about complete graphs. A complete graph is one where we have some number of points, and every point has to connect to every other point. So for example, I could draw it like this, and this point could also connect to this one, but if I wanted this one to connect to this one, instead of going straight across, if I wanted to keep it what we call planar, i.e. lines not crossing, then I could go around the edge. There we've got all 4 points connecting to all 4 other points. However, if I wanted to add in another point, no matter where I add it, so if I add it here, it won't actually matter, I can't connect it to every other point. So there, 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 but I won't be able to connect it to this one. The original one we drew we call K4, complete 4, whereas this one, which we were trying to go for, K5, doesn't exist, and there's just no way of doing it. Often when we're proving something in graph theory, if we can show that something is equivalent to try to draw K5, then we can't do the original problem. That's what's going to occur in a minute. So, the problem is this. We're going to keep adding numbers. We're going to keep adding numbers into our graph. So, for example, I'm going to start with the number 2. Start with it in the middle. I tried this a minute ago on one board and it got a bit messy. So this is a 2-board problem. I'm going to start with the 2 right in the middle because it's going to connect to lots. Every time I add a number in, and I'm going to keep adding the natural numbers, except for one at the start, I'm going to join them up to any that they share a factor with. So for example, the number 3, we do it there, doesn't connect to 2 because they don't share a factor. Yeah, so if one is a factor of the other one, then we're going to join them up. The number 4 connects to the number 2, like that. Yep. And we keep going. The problem is, what is the last number we can add? Or phrased a different way, what's the first number that we are unable to draw the lines with the lines not crossing? So let's carry on. Do 5 over here, perhaps. 6 will connect to both 2 and 3. So I'm going to do it there. 2 and 3. That's fine. It's going to get harder as we go along. So 7, I'll do over here. 8, well, that connects to both 2 and 4. So we've got a little triangle of them going over here. 9 is going to connect to 3. Try it there. 10 will be 2 and 5. So I can go directly in between them. It's looking fine. 11, prime. I'll just stick it over there somewhere. 12, that's quite factor dense. So we need 2, 4, 6 and 3. I'm going to try sticking it here. So 4, 2, 3, 6 and 3. 13, number prime, I'll just stick it over here somewhere. 14, so we need 2 and we need 7. So it's going to go directly in between these two. Some of these I might have to rub out things to be able to rearrange a bit. 15, we need 3 and 5, so there and there. So I'm going to do it here, 15, 5 and 3. 16, power of 2, so 2, 4 and 8. I'm going to stick it in the middle. 16, 2, 8 and 4. Notice if we had 32 as well, the next power of 2, we'd have to have a complete graph of 2, 4, 8, 16 and 32. So that's definitely not possible to do. It'd be trying to do K5 again. So we won't be able to do 32, but actually we're going to falter before that point. 17 prime, I'm going to stick it here. 18, so we need 2 and 3 and 6 and 9. So 2, 3, 6 and 9, I'm going to stick it in here. 18, It's starting to get quite connected. 19 is prime. Yep. 20, ugh. So 2, 4, we're going to need a 5 as well. and we're going to need 10, which is there. So I could do it on the outside. So 20 would be the 4, the 2, the 10 and the 5. Okay, that just about went in. 21, we need 3 and 7. Now, I'm going to have to rearrange some stuff. 3's over here, 7's over here. But if I move this branch to over here, then I could fit 21 in here. So I'm going to switch it. So here's 14, here's 7. So I can now rub out those. No, I regret using 2 boards. So that's going to be 21. And we've got that little branch there. So it's still fine, I've just moved where it was. It's still got the same structure. 22, I need 2 and 11. Well, if I swap that 11 there to over here, because it wasn't connected to anything, that would be 22. And we can have that chain going there. 23 is prime. Now, 24 is the first one we can't do. Now, 24 has the factors 2, 3, 4, 6, 8, and 12. Well, the factors that we care about this 3 also has 1 in itself, but whatever. Right, the way we're going to do this is we're going to show that trying to put it in is the equivalent of trying to do a complete 5 graph somewhere on here. If we look at 2, because that's a super connected one, 6, 12, and 3, they have this structure. Da, 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 da. So it doesn't really matter where the points are, but here was 2, here was 6, here was 12, and here was 3. Oh, sorry. There you go. So 12 was here, 3 was here, 6 was here, 2 was here. It's not quite the K4 graph, because at the moment 2 and 3 weren't connected. But they were indirectly connected, because 2 connected to 18, which connected to 3. So it's like this one here, dot, 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 dot. It's like a pseudo line between them. It just happens to have an 18 in between them. It doesn't really matter because it's still forming a barrier. So it's like we've already got a K4 graph between these things. So if I needed to add another point, that's the equivalent of trying to add one more point to make a K5 graph, which we know is not possible. So it's not possible. So 23 is the last number that we could add in, or 24 is the last one. 8 is the first one that we can't add in. Proved. Done. Cool.